All right, so for this first lesson looking at population tests, the main focus is understanding what a Z or a Z test and a T test are and how they're similar or different from one another and when to use them. So in general, both these tests are for making conclusions about a population based on its sample. And depending on what we know about the population, determines if we want to use a Z test or a T test. In general, if we know the standard deviation of the population, we'll use a Z test. If we don't know the standard deviation of a population, we'll use a T test, and we'll base it on the standard deviation of the sample, which is generally not as reliable. So we have here a good old peanut farmer, and they package peanuts in 25 kilogram bags. However, he's received a complaint that the bags do not have 25 kilograms. So to investigate this, and it not being reasonable to measure every single bag, takes a sample of 6 bags, and we can see the sample weights here. All right, and from this, we want to try to determine some conclusions about the population, in this case, all the bags of peanuts, and trying to determine, does it seem fair, this complaint, that the mass of these bags is actually less than 25 kilograms? Or is this just a reflection of the sample we've taken? Because keep in mind, the smaller the sample, the more variety there is, and the more it may vary from the actual population. So it says here, if the weights of the bags of peanuts are normally distributed with a standard deviation of 1.5 kilograms, so we know right now we're going to use the Z test, calculate the p-value and use this to determine whether at a 5% level of significance, the mean weight is likely to be less than the required weight. And so, first thing we want to do is, like I mentioned, that we want to use a Z test because we know the standard deviation of the population. So use a Z test because we know the standard deviation. Okay, in fact, I'll even write it in. And we know the standard deviation of the population is 1.5 kilograms. All right, the alternative hypothesis is given, so I'll state the null hypothesis, which would be H naught, which would be that the mean is 25.0 kilograms. And the alternative hypothesis is that it is less than. That's what we're trying to see if that's true. All right, so not only do we want to perform a Z test here, we want to perform a one-tailed Z test, because if I think about a normal distribution here, here's the mean. We're trying to see just, is it, we're trying to look at what's the probability that it'll end up far away from the mean to the left. We're trying to find values that are less than the mean. And so we'll call this a one-tailed t-test to the left, where again, we're trying to determine is the probability of the mean is going to be less than 25 for the population given this sample. All right, at this point, it's GDC work. We know, again, it's going to be a Z test. In this case, we have the data, so we want to go into our GDC and input these 6 values, tell it that we have the data already. We will also tell the mean of the population, at least for our null hypothesis, which is 25. We know the standard deviation. So again, for null hypothesis, we presume all that's true. And we should pretty quickly get the probability of a sample coming up like this. And so the p-value we get is approximately 0.332, which recall that means there's approximately a 33% probability that we would get a sample like this, assuming the mean of the population really is 25. That's it. This is above the significance level, so we should fail to reject H naught. Remember again, we're not saying that H naught has to be true. We don't have enough evidence to say that it's true. Sorry. Fail to reject H naught because this is far greater than 0.05. Oh, wrong symbol. There we go. All right. Other than that, I will just make one little comment. We look at the stats for this sample, the mean of the sample is approximately 24.7 kilograms. right? So the mean of the sample was less than 25 kilograms, but we don't have enough evidence to say that the actual population must be less than that, because it was just a sample of 6. The larger the sample, the more, if we had, for example, a sample of 50 bags and we had the same mean of 24.7, then we probably would find that we would actually reject H0. However, the second part is, okay, what would be the critical value? In this case, what would be the maximum weight we could have in that for the sample mean, such that we would have to reject the null hypothesis? Or if I look back to my visual, if this area is going to be 0.05, or if this is going to be 5% of the region, what value would have to go right there for the sample for this to, for us to actually reject H0? As we can see from the first part of the question, we had a sample mean of 24.7, and it was too close to the mean, or was too large for us to reject H0. But what would the value be? Well, to do that, first we got to remember that when we're dealing with a sample, the standard deviation of a sample is not the same as the standard deviation of the population. And so if we're looking at the sample here, sample pop mean will be normally distributed. The mean of the sample we expect to be roughly the same as the mean of the population, whereas the standard deviation, or actually I'll start with the variance of the population of the sample, we expect to be the variance of the population divided by the sample size. And that's something we learned earlier in this. So for this particular situation, I'll substitute in the mean is still 25. The variance is 1.5 squared over the sample size, which is 6. So for this case, if I look at these details, that means the mean of my sample, we would expect to be 25, and the standard deviation of our sample, we would expect to be 1.5 squared over 6. Sorry, that's the variance. I got to square root the whole thing. There we go, which comes to 1.5 over the square root of 6. And with that said, I can now use my GDC with the inverse normal function to figure out what value would have to go right here so that this region would be 5% of the total, or have an area of 0.05. And knowing that the mean is 25, which is all going back to our null hypothesis. And so at this point, we want to use the inverse normal function on our GDC, in which we tell the mean is 25, the standard deviation is 1.5 divided by the square root of 6, and we'll say the sample size. The sample size was just 6. Actually, I don't think we have to say the sample size for that. And sorry, I don't need a sample size. We need the area. And so the area of the region we're looking at is 0.05 because it was a 5% significance level. And again, we only want a left-tailed, and we should get on our GDC pretty quickly. We should get a critical value of approximately 24.0 kilograms, which means if the mass of our sample was less than or equal to 24 kilograms, then we would actually reject H0 and accept the alternative hypothesis that the mean weight of the population is less than 25 kilograms. And so that is a sort of, we call that, again, the critical value. And that was all by using our inverse normal function, but connecting it back with what we've learned about how this variance and standard deviation of a sample is not the same as the variance and standard deviation of the population. And with that said, let's look at this. This will be a question which we'll use a t-test, because if we look at this question here, we'll see we do not know the standard deviation of the population. So we have here our, what is this, 15 bags of cement. And the factory producing them intends their weight, the mass, to be 60 kilograms. But they do not know the standard deviation of the weights of the bags. So the test the population mean, they have collected this data, these 15 samples. So we want to determine if as it says here, if the mean weight is less than 60 kilograms. And that's key to be clear on what we're trying to test here. We want to test, is the mean weight of their population less than 60 kilograms? It's intending to be 60 kilograms, but maybe it's not. But we have to go on is the sample. So let's first state the hypotheses. So, and I mentioned we'll use a t-test because we do not know the standard deviation of the population. So the null hypothesis will be that the population mean really is 60. The alternative hypothesis, not high, hello. The alternative hypothesis will be that the mean is less than 60. Because if we look at the question, that's what we're concerned about, is the mean weight less than 60? Similar to the first question. Don't assume anything. It all goes back to the context of the question. Other than that, this is pretty quick because at this point, we want to run a t-test, like I mentioned already. We want to input the data. So we have 15 points of data we want to put into our table. Run a t-test, tell it that we are using data instead of summarized statistics. And we should pretty quickly get a p-value of approximately 0.361, which means there is approximately a 36% probability of getting a result like the sample if the mean of the normally distributed population really is 60 kilograms. Well, that is well above the 5% threshold. So once again, we fail to reject H0. There is not enough evidence to say that the population mean really is less than 60. Other than that, before we get to the last question, just keep in mind that's the main differentiating aspect between a t-test and a z-test. One involves knowing the standard deviation of the population, one doesn't. All right, last question is what we call a matched pair problem. We have two sets of data and we want to see how they compare. So we have students in a science class feel they did not score well on an exam, so in response, the teacher spent a few class periods reviewing the material and allowed them to take the test again. So we want to see here now, did that review make a statistically significant difference in improving their marks? So for a question like this, we want to compare these two sets of data. So for this, what really matters is not so much the actual data points here, but is the difference. So I'm going to take this table and add on to it. And we want to see how the second exam marks compare to the first. So I want to go the second exam, take away the first to see how much they ideally improved. And so, for example, this first student went from 54 to 67, so it's a gain of 13. Then we went up by 7, up by 2. This person did worse, so I put negative 3. My apologies for that. Up by 13, and so on. So these are the values that we'll actually want to pay attention to for a matched pair question like this. This difference. All right, so I want to state the null and alternative hypotheses. So as usual, our null hypothesis will be that the change in the difference, the average difference will be 0. The null hypothesis will be that it did not make a change or not a statistically significant change. Keep in mind that mu there, you see that average, that's the average of the difference. With that said, our alternative hypothesis will be that it was greater because we're trying to determine here if it really helped the students or not, whether it helped them. And so I'm concerned, hopefully it made a statistically significant improvement, but that's what we're trying to see. So the null hypothesis is that the mean is 0 of the difference, and the alternative hypothesis is that it's greater than 0. I just realized I spelled difference wrong here. Difference. I'm going to stick with it. New word, difference. All right. With that said, things are pretty quick here. We want to use a t-test because, again, we don't know the standard deviation. We have the data, so we're going to input this information into our table. With a t-test, we want to use a t-test in which we're trying to find if our value is greater then 0, 0 being our mean we'll have here, because we're trying to find the difference between it. And we should pretty quickly get to a p-value of approximately 0.0551, which is just above a 5% probability, which, keep in mind, the significance level was 5%. So we're close, but not quite. Based on the significance level, we have to, again, it's the theme of today's lesson, fail to reject H naught. There is just barely not enough evidence to say that the review made a statistically significant improvement. Although, again, this is very close to that level there. But going with our predetermined significance level, we have to fail to reject H naught. Although, keep in mind, this was what? Just 1, 2, 3, 4, 5, 6, 7, 8 students. Potentially, if we looked at a whole class of 20 to 30 students, maybe we would find the p-value would actually go below and we would actually reject it. But from what we have, we don't have enough information, so we have to fail to reject H naught.